Okay, we'll walk through the solution to quiz 1 in MENG 2240 Mechanics of Materials. So in this problem, we're given a beam that is simply supported on both ends, and we have a distributed load here. This 4 kilonewtons per meter distributed load that's going down to 0 at point B, and we're told to find the internal loadings at a cross section through point C. So we're going to take a section at point C, cut it this way here, find what our internal shear, our normal force, and our bending moment is at that point. We're also told to assume those reactions at the supports are vertical, and then finally there's a rubric or a discussion of how we earn points for this problem. So we can see from the rubric that there's a few hints here. We need to draw a free body diagram for the entire thing, free body diagram for the section that we're going to consider, find equal reaction or a reaction or both reactions for the entire body, set up some equations of equilibrium at point C, and then finally solve for those internal loads. So let's get started. So our free body diagram for the whole beam. Here's our beam. At this point we have a force AY. On the other end we have BY. Those are a total of 6 meters apart. So we have 1.5 plus 3 plus 1.5 gets us our 6. Our distributed load is 4 kilonewtons times 6 times 1/2. 1/2 base times height for that area of that triangle. So then that's going to be operating a third of its distance from the higher end. So at this point we'll have that equivalent concentrated load, which is 4 times 6 times 1/2. It's going to be 12 kilonewtons. And that location 6 over 3, so 2 meters from point A. Point C is still in here at 1.5 meters. Just keeping that there for housekeeping. And that takes care of our distributed load turning into a concentrated load. Our reaction forces are on here. So everything we need for our free body diagram is at this point. So there's step 1, our free body diagram. Gets us 1 point. Now we'll find our reactions. So depending on how we want to solve this problem, we'll either need a reaction at A or a reaction at B. We won't need necessarily both. I'll solve both as I'll do both sections as an option to illustrate how we could have solved this problem either way. So I'll start with the moment around A. It has to be 0. What does that moment look like? We'll have 12 kilonewtons at 2 meters. It's creating clockwise motion, so we're going to have negative 12 kilonewtons times 2 meters plus BY at 6 meters. So it becomes 24 on the left side divided by 6. BY 24 kilonewton meters or 6 meters goes to 4 kilonewtons. There's one reaction, and then the other direction then the other equation we'll write here. Sum of the forces in Y equals 0. So we have negative 12 kilonewtons from our concentrated load plus 4 kilonewtons at B plus AY. Pull those to the other side. AY equals 8 kilonewtons. So either one of those will get us 1 point. Alright, so then we have our choice. What section do we want to use? So we could section this at C here and take the left side and have that AY to C section. If we do that, we'll have this distributed load here, and it won't go to 0. It'll still have some value at this side. So that just means we'll have to find 2 equivalent concentrated loads and apply those in our free body diagram. Or we could take the right hand side from C to B and have this distributed load that starts from some value and goes down to 0. I'll do both ways. So step 1, or the first way we'll do it, we'll do the section A to C. So my diagram there, I have AY 8 kilonewtons. At C I have my normal force, excuse me, and then I have my shear, which is going to be down, VC, and my moment, which is going to be causing the beam to smile. So those are my internal loads. And then what is my distributed load? I'm just going to sketch it in here, the shape of it. So at this point it's going to be 3 kilonewtons per meter. At this point it's 4 kilonewtons per meter. How did I find that? Well, I knew C is 1.5 meters away from A, and the total thing is 6 meters, so that's 1/4. So taking 4 times 3/4 gets me 3 for the value at this point. So I actually have 2 distributed loads, if you will. So I have this part, the rectangular part, which is going to be 3 kilonewtons times 1.5 right in the center of this beam. So I'm going to have 3 times 1.5, 4.5 kilonewtons at 0.75 meters. And then I have this other section, that top little triangle that goes from 4 to 3, excuse me. So 1 kilonewton per meter times 1.5 kilonewton meters times 1/2, because it's a triangle. So at 1/2 a meter, I'm going to have another load, and this guy is going to be, there we go. So we have 1 times 1/2, 1.5, so 1.5, 0.75 kilonewtons at 0.5 meters. So that's my free body diagram. Get a point there, and then we can write some equations. So some of the forces in Y equals 0. So what do I have there? I have 8 kilonewtons from my AY. I have minus VC. I have minus 4.5 kilonewtons. And I have minus 0.75 kilonewtons. So then I have VC comes onto the other side. VC 8 minus 4.5 leaves me with 3.5 minus 0.75, 2.75 kilonewtons. So that means my direction for that arrow is correct, so it is down. Then I can do sum of the moments at C equals 0. So what do I have here? I have negative 8 kilonewtons times 1.5 meters. And then I'm going to have counterclockwise motion plus 4.5 kilonewtons from my main rectangular load at 0.75 meters and plus 0.75 kilonewtons at 1 meter from C. So this 0.75 kilonewtons is half a meter from this side, which means it's 1 meter from C. And then I'm going to have plus MC. So that whole thing equals 0. So what do I have? I have 12 kilonewtons. Move that to the left. Subtract off this thing. Subtract off that thing. MC, if I do my math correctly, is going to be 7.875 kilonewton meters. The 3 significant figures, that's 7.88 kilonewton meters. And then finally, almost goes without saying, but it's required, sum of the forces in X equals 0 equals NC. So my normal force at C is 0, which you probably figured out from just looking at it. So that would be my choice if I went with section AC. So you have these equations of equilibrium here. giving you 1 point for each of those. I'm not going to give you a point here, and then these values here, all 3 of them together gets you 4 points. So there's 6 points really in this section. So 6, 7, 8, and then 9. I must have skipped a point here somewhere. My free body diagram at C was 2 points, sorry. Alright, so another way I could have done this is section C to B. The math is a little more straightforward here. So here's C, here's B. My reaction at B was 4 kilonewtons up. My distributed load in this case does go to 0 at the right side, and this is 3 kilonewtons per meter on the left, 0 on the right. This length here is 4.5 meters, so I have 3 times 4.5 times 1/2, so that should get me 6.75 kilonewtons, and that's going to be, it's going to be 1.5 meters from C. So I didn't have to break that distributed load into 2 parts. And then I have my normal at C. I have my shear, it's going up, VC, and then my moment is clockwise, positive bending clockwise for that. Still a negative moment is my equations of equilibrium. So there's 2 points for that. So then we'll use some equations of equilibrium. Some of the forces in y equals 0 equals negative 6.75 plus 4 kilonewtons. Drop my units there. Plus VC, that all equals 0. So as I pull that to the other side, I get 6.75 minus 4. So VC 2.75 kilonewtons, which is the same I found the other way. Then we'll do the moments. Some of the moments around C, 0 equals, so we have negative MC. This concentrated load from our distributed load is going to be creating a negative moment, minus 6.75 kilonewtons. And that's operating at 1.5 meters from C. And then finally plus 4 times 4.5, squeezing that in there, from my B. So this thing is, let's see, this is about, what is that, 18, and this is a little more than 10. So MC equals 7.875 kilonewton meters, which to 3 figures is 7.88 kilonewton meters. And then finally, some of the forces in X equals 0 equals NC. So there you have, we get the same result. This was a little more straightforward. We didn't have to break the distributed load into 2 parts, but if we were careful, we could have gotten the same thing taking the A to C section. So hopefully that clears up any of the errors you may have made in your quiz, and look forward to seeing you in class.